Hi class, this is example 3 for 4.5. Use the linearization 1 plus x to the k power, which is approximately 1 plus k of x, to approximate the following. State how accurate your approximation is, okay? Remember, this is the approximation for powers or roots, okay, near 0 when x is close to 0. So how would I use this? What are they asking you to do? What they are asking you to do is, number one, would you agree that this is a power function? Okay, so you want to rewrite it in that format. 100 is your k, and it says 1 plus always. So what is this x value that's near 0? This x value that's near 0 is 0.002, okay? So, and I need to, so what is k? K is 100. Okay, because that's your power. X is a small value near 0, 0.002 based on your math here. So with that, I'm going to plug it in my formula. K is 100, X is 0.002. So by approximation, 100 times 0.002, I can move the decimal over, so that's going to be that, and that comes out to 1.2. So my approximation is when X is 0.002, okay, then the output is 1.2. Now, how accurate is it? Okay, so what that means is I need to go and find the actual value. Here's the actual value. Okay, what is 1.002 to the 100? Let's go. Where's my calculator? Clear. 1.002 to the power of 100 equals 1.2211. Okay, so let's go back. Oh, you know what? Let's just subtract my 1.2 to see, back, 1.2 to see the difference. So the difference is 0.0211. Okay, so let's go back to my notes. When I subtract 1.002 to 100, subtract my approximation answer, the difference came out to be 0.021158 and some dots, okay? As you can see, if I were to write this as a scientific notation, is 2.1158 times 10, because I can just move the decimal 2 places, to the negative 2, which means this is definitely less than 10 to the negative 1, okay? And 10 to the negative 1 is like 1 over 10, so 1/10. So the difference, okay, is really small. 1/10 is from the actual value, so it's not bad by approximation. Okay, and as you can see, the approximation is so much easier to do. I don't even have to use my calculator. Okay, so that's why we use calculus, because oftentimes it's just the difference is so small, it's not significant, and it's just easier to use calculus to find them. All right, let's do this one. And again, I'm going to write this as a power function, 1.009 to 1/3. Okay, that tells me k is 1/3, and if you rewrite this as a 1 plus 0.009 to 1/3, that tells me x is 0.009. Okay, so by the approximation rule, it says 1 plus k, which is 1/3, times 0.009 for x. Okay, so that's going to give me, let's see, 1.003. So by that calculation, that's my approximation. Now I'm going to need the calculator to do 1.009 to the 1/3 power to see the difference, and then subtract it, okay? Clear. 1.009 to the power of 1/3. Parentheses, 1 divided by 3, close that. Okay, so 1.0 and then minus 1.003. That gives me, okay. Because remember, the difference is an absolute value, so you don't need to worry about the negative 8.95. So the difference in approximation is 8.955 times e. Okay. So when I find the difference is 1.009 to the 1/3, take away my approximation, which came out to be, the calculator says different because I've used an absolute value. I don't need to worry about it. 8.955 times 10 to, was it negative? What was that? 10 to the negative 6. Okay, so 10 to the negative 6. Okay, negative 6. So, wow, this one, the difference is really small. Would you agree? Okay, so it's not even a big deal at all. All right. So the difference is less than, definitely less than 10 to the negative fifth. Okay. Which is, oh my gosh, 10 to the negative fifth, that's like 5 zeros on the bottom, right? 1, 2, 3, 4, 1, 2, 3, 4, 5. That's like 1 out of like 100,000. So the difference is so small, but the work was so much faster. Okay, so there you go.